Thank you, Avi. So this talk is going to be about a new type of regularity lemma. It's a joint work with Asaf Shapira. So let me give you some background about the regularity lemma and applications of it. So here's the informal statement. Every dense graph, by dense I mean it has, if there's n vertices, it has, I don't know, 20% of the edges or something along these lines. So not literal of n squared edges, has a small equipartition, so a small partition of its vertex set into equal size sets, so that almost every pair is quasi-random or epsilon regular. So what do I mean? Basically, you can, whatever graph you are given, you can cluster the vertices in some way, so that it looks basically like that. If you take a look on almost any pair of Vi, Vj of clusters, the induced bipartite graph between those two clusters behaves like a random graph. So it's very easy, what's going on there. Formally, this is the definition of an epsilon regular bipartite graph. For every subset x of Vi large enough, at least epsilon fraction of it, and every subset y of Vj large enough, the density between x and y, so the normalized number of edges between x and y, so dxy is the number of edges between x and y divided by the total possible number of edges, which is the size of x times the size of y. So the density between x and y is just like the density between Vi, Vj themselves, the two clusters themselves, up to some error epsilon. Okay.
What does this equipartition mean?
All the parts are essentially of the same size.
It doesn't matter, are essentially the same size.
Yeah, up to 1 or something, whatever.
How many parts doesn't matter?
So that's the main point of it. This number of parts has to be is small. What do I mean by small? Independent of the number of vertices in the original graph. Only depends on this parameter epsilon, the quality of the regularity. An intuitive way to think of that is that basically the regularity lemma gives you a way to compress your graph. So now consider a small graph where every vertex corresponds to a cluster here. And you put an edge between the vertex Vi and the vertex Vj with weight, whose weight is the density between Vi and Vj. For irregular pairs, there's a fraction of irregular pairs. For them, you just don't put an edge or whatever. And the intuition is that you can, for many purposes, you can just look on the compressed graph, which is tiny, and study whatever question you have in mind for that graph, and deduce something for the original graph with some error that depends on epsilon. Why is it enough to just look on for many purposes, why is it enough to just look on the compressed graph? Simply because what hides behind an edge in the compressed graph? A bipartite graph which behaves as you would expect, like a random bipartite graph. So nothing too interesting is going on there. Okay? So I would actually need, this is the informal statement, let me write something slightly more formal because I will need this. Yeah.
You have to say it's amazing.
It is amazing.
Every graph has such a simple small model.
It's right.
It's a constant size model.
Right. So why, by the way, why do I say, so I do write every graph, but why do I add dense there in parentheses? If the graph is not dense, then the size of the partition is not so small now. And okay, I'll explain in a minute, but so if the graph is not dense, it's true. I'm not saying it's not true. This is why dense is in parentheses, but it's not interesting. The number of parts can be larger than the number of vertices. Well, this is simple.
No. There's another interpretation. You can say that the empty graph, I mean the partition in which all of them are, all the weights are zero, also approximates.
Sure.
Yeah. So that's you don't have to think. You can have one part.
So the bottom line is that it's not interesting if your graph has n log n edges or something like that.
Because epsilon is constant.
Okay, so let me write a statement more or less. So the statement is as follows. For every parameter epsilon and every graph, you can find this model, this small partition. So there exists partition. In fact, I'll write equipartition. All the parts over the same size, Vi of the vertex set of G and denote the number of parts by m of epsilon, so a function only of epsilon, such that for all but at most epsilon fraction of cluster pairs Vi, Vj, we have that the induced bipartite graph between Vi and Vj is epsilon regular. That's it. Every graph is a small model. Or a small compressed graph. Okay. As an exercise, just to say that we follow this definition, what if I were to remove all the edges between cluster pairs that are irregular, that are not guaranteed to be regular by this statement? How many edges do I remove in this way? Okay, so let's calculate this.
You also want at least so many partitions or something like that?
Yeah, so I will need, okay, notice that, so the swastika asked, what about, do I need to also require a lower bound for the number of parts? The thing is that I don't require, I'm not being 100% proven, but a priori I don't require anything for the case where I equals j, so for the number of edges within, what's going on within a cluster. So for this to be non-trivial, you at least want this partition to have at least 2 parts, for example. And it's customary, by the way, to require that then the partition has at least, say, 1 over epsilon parts. In this way, the number of edges, the total number of edges lying within clusters is small. So you might as well ignore them. And so the guarantee of semi-ready applies to basically most of the graph. Okay, but I will ignore this tiny point. So here's the exercise. What is the total number of edges in irregular pairs? Let's see. What is the number of irregular pairs? It's at most an epsilon fraction of the total number of pairs, so that's at most epsilon times m squared, right? And the number of edges, give me an upper bound for the number of edges between any given such pair of clusters. Well, it can be like a complete, I have no idea what the density there is, so it can be a complete bipartite graph. So you would have there n over m squared edges, potentially. So that comes up to epsilon n squared edges. So if you are fine with removing this many edges, then basically you can guarantee that there are no irregular pairs, because now whenever there was an irregular pair, I removed all the edges, I get an empty graph which is trivially regular. Okay, so keep that in mind. I'll come back to this in like 20 minutes. Okay, let's move on. Now that we know the definition, let's talk about important applications. The regularity lemma is so important because it has so many important applications. In fact, many classical theorems in graph theory, also in computer science, for example, also in geometry and number theory, all of them follow not like relatively easily once you have this modeling of the graph, once you have this compressed graph, the regularity lemma. So one nice application is to the problem of approximating max cut. So this won't be terribly important for the rest of the talk, but let me just say a few words about the max cut problem. So the problem is as follows. It's the following computational problem. You're given a graph and you want to find a partition of the vertices into 2 parts, so that maximizes the number of edges in this cut between the 2 parts, or equivalently you want to find a subset of the vertices that has the most outgoing edges coming out of it. So computing this number in general is an NP-hard problem. It's even not just computing exactly, even just approximating this number to some constant fraction, constant ratio is NP-hard. What is that ratio? Well, that's very much dependent on the question whether the Unigames conjecture is true or not, but I don't care about that. What I will care about is the problem max cut, where I require that where I tell you that the input is guaranteed to be a dense graph. Turns out that for such graphs, you can approximate arbitrarily well the max cut. And you can easily prove this from the regularity lemma. Roughly, the idea is that you apply the regularity lemma with parameter epsilon, and if you want, that will basically give you a 1 minus epsilon approximation of max cut on this graph. So you compress this graph using the regularity lemma, you get a graph on roughly essentially a constant number of vertices, and you just solve max cut there. Of course, it's a weighted graph, so you need to solve weighted max cut. But you solve max cut there, and it's not too hard to show that this max cut in the compressed graph gives you, after normalization, it gives you the same max cut in the original graph plus minus some epsilon. So that's a great question. So we actually want an algorithm, and it turns out that you can find these partitions, a regular partition, in time which is definitely polynomial in the number of vertices.
It's another result way beyond the
So actually, now that you know this, is it true that the STP algorithm also does one?
That?
Is it true that the semi-definite programming algorithm also gives 1 perceptual approximation? Or it's we don't know that?
Come again, you're asking if semi-definite programming gives you what?
Does that also give a 1 perceptual approximation?
1 minus epsilon, I mean, it's like I wouldn't say equivalent, but two different ways to get pitas for max cut. Yeah. On dense graphs, of course. For graphs of density and log n, this obviously doesn't work, and in fact there's no approximation algorithm. Assuming p equals does not equal np. Okay. Another application is to approximate the number of induced copies of some fixed graph. I won't talk about this in detail. From combinatorics, you have the question of Ramsey number of all bounded degree graphs, or graphs of degree at most 10. So the first result that showed that this number is linear was proved using a variant of the regularity lemma. And the graph removal lemma, arguably the most important application of the regularity lemma, and also one of the first applications. I will talk about this in more detail in a few slides. Importantly, the graph removal lemma by itself suffices for other applications, such as semi-reduced theorem on arithmetic progressions, for example.
Or approximating the number of copies of some graphs.
Right, or also property testing if the graph is free of copies. I will talk about that in a second. And also another application is to the hypergraph regularity lemma, which is proved by iterating the graph regularity lemma. I won't talk about this in detail, but what I do want to mention is that the bounds that you get for each of those applications and others, the bound that you get for whatever the precise question is in every application, the bound that you get very much depends on the number of parts, on the bound that you have in the regularity lemma. Hence, it's very important to get a small partition, or to know what is the best possible bounds you can get on this M of epsilon. Okay, so here's the definition of M of epsilon. The original proof by Semeredi of the regularity lemma gave the following bound. So that's a tower of height roughly 1 over epsilon. So that's more than an exponential function 1 over epsilon. It's more than double exponential. So it's 2 to the 2, and the number of the number of 2's is roughly 1 over epsilon. And for 20 years, people have wondered whether Semeredi's proof can be improved, and Gauss showed that essentially no. So Gauss actually constructed a graph so that every epsilon regular partition of that graph has to be that large, roughly. Okay. Which brings up the question, since the bound here on M of epsilon is so horrible, can you actually deduce the applications not from Semeredi's regularity lemma, but from some weaker regularity lemma, whatever that may be? The answer is that for many applications, yes. So, for example, the max cut application that I mentioned for dense graphs, you can actually prove it by using the weak regularity lemma of Friesen-Kahneman. In an hour from now, I will define what the weak regularity lemma is. Right now, we don't need that. For the second,
The bound is exponential.
yeah, so I'll talk about bounds in a second. For approximating the number of induced copies, you can use what's known as the cylinder regularity lemma, it's very important. And for the Ramsey application, you use something which is like a one-sided regularity lemma. Again, I won't talk about that. And as Avi mentioned, all the bounds here are not tower, but actually just a single exponential in 1 over epsilon. Much better. And by the way, for example, for the regularity lemma, this is known to be optimal. But you might notice that two of the applications that I mentioned are missing, the last two applications, the removal lemma and the hypergraph regularity lemma. So what about them? There's a good reason why they're not on the list. Let me tell you about the graph regularity lemma. I will actually consider a special case the triangle. Sorry, the graph removal lemma, and I will consider the special case of the triangle removal lemma. So this is a statement by Rosa and Semeredy, actually predating the 78 paper by Semeredy. They use a slightly earlier version of the regularity lemma to prove this, but not very important. Here is the statement. It says that the following: if your graph has roughly n squared edge disjoint triangles, then the total number of triangles that it has is roughly n cubed. Okay, you can't pack into a graph with n vertices order n squared edge disjoint edges without creating tons and tons and tons of triangles. In particular, one additional triangle, but also a cubic number of triangles. In computer science lingo, this is basically a property testing statement. So the property here is the property of a graph being triangle free. And what does it mean testing it? What does it mean that it's testable with a constant number of squares? It means that if you want to decide whether the graph, so the setting is that you are given a graph, but not explicitly. You are given a query access to the graph. Okay, you can query pairs of vertices and ask, like, is there an edge between those pairs of vertices or not? And the question is, given such a graph, query access to this graph, can you decide whether the graph satisfies this property of being triangle free or far from it? Of course, if the graph if the graph has a single triangle, then with a constant number of squares you won't be able to find that triangle. So always the question in property testing is either does the graph either satisfy the property or far from satisfying the property. Far in the sense that epsilon far means that you must remove epsilon n squared edges. Okay, so if you actually think about it, the removal lemma immediately gives you a very simple algorithm. Here's the algorithm. Just uniformly at random, choose a triple of vertices and see whether there's a triangle there. If there is a triangle there, obviously the answer is that no, the graph does not satisfy the property. It's not triangle free. We found a triangle. What if we just weren't lucky and there wasn't a triangle on the three vertices that we chose at random? But the thing is that the removal lemma guarantees that the total number of triangles, or if you divide over by n cubed, the probability that you will see a triangle is constant, 1 over this function of epsilon, rem, short for removal of epsilon.
What is that function?
Some function so just notation, just function that depends only on epsilon. It is constant. That's the question. The question is, what is this function? Why is this important for this application? Exactly because this gives you 1 over rem gives you the probability that those three vertices span a triangle. But since this is going to be a constant, think of this as a constant probability, assuming that epsilon is constant, then
constant is small as you want. You pick this constant.
Right, it's not a fixed constant.
Error of your probability.
So simply repeat this random process, choose triples of vertices and check whether they span triangle, rem of epsilon times 10 times that. And that will guarantee that with probability 99% you are going to witness a triangle if indeed there are many triangles, or if indeed the graph is far from satisfying triangle freeness.
The amazing thing is that it doesn't even depend on the size of the graph.
That, sorry?
Does not depend on
It doesn't depend on the size
Yeah, of course. So as I said before, the intuitive way to think about it is that if your graph contains order n squared, omega of n squared edge disjoint triangles, which is essentially like saying it's far from being triangle free, right, you need to remove one edge at least from each triangle to get rid of all the triangles. Then the total number of triangles is omega of n cubed. Okay, this omega depends on epsilon in some unknown way. The question is, what is this way? So what about?
In a different way. I mean, in the way the original user summarily said it. I mean, it's an equivalent way, but it's sort of stunning to me. I still cannot comprehend it, even though I know the proof. It says that suppose you want to build a graph with a quadratic number of edges, that on any 6 vertices you will not see more than 2 triangles. It's impossible. It looks possible, you know, it looks like you make this quadratic very small, so, you know, every 6, it looks like some probabilistic argument. It's impossible.
Mm-hmm.
Every graph in which on every 6 vertices you have at most 2 triangles necessarily has sub-quadratic number of edges. It's equivalent.
Mm-hmm. Another basic thing is that this implies, not equivalent, but this implies Semmelweis theorem on arithmetic progressions for three-term arithmetic progressions, and a priori it's very surprising. And this is a statement about graphs or about property testing of triangle freeness. But if you construct the appropriate graph, then you can actually reduce one question to the other somehow. Okay.
This 6 vertex property is easy to see. Why does it?
Just a union of.
Related to what you said about linear number of triangles.
Just yeah.
Completely maybe, so fine. But then 6 vertex thing, like
Whether it takes a minute to see this. It's not exactly trivial. Okay. So what about bounds for the triangle removal lemma for this rem of epsilon function? So you can actually use Semmelweis regularity lemma, as I said before, to prove the removal lemma. I will not give the proof now. I will give even a stronger proof later. But the bound that you get is essentially the same bound as in the regularity lemma, which is tau of poly 1 over epsilon. And this cannot be improved if you use the regularity lemma, as Gauss showed. As what about lower bounds? The best lower bound that we know on this function REM is essentially polynomial in 1 over epsilon, slightly super polynomial. So this is the gap between not something which is polynomial and exponential, between something which is essentially polynomial and a Tower function.
So what's the best bound node for Ross theorem again?
It's different.
It's better than that though. It's better than 1 over epsilon.
Right. I have in the last slide here the exact bounds. If I will have time, we'll talk about this reduction. It's known that this is not equivalent to Roth's theorem is the Semmelweis theorem on arithmetic progressions for 3-term arithmetic progression. And the bounds there are better than the removal lemma. So the removal lemma is probably not equivalent to.
Yeah, that's why I was asking.
Right.
They were equivalent, but they're not actually equivalent.
No, definitely not. Okay, so here's the question. What about, I want to improve the bound that we get from the regularity lemma. What about if I allow modifying small number of edges, so add or remove a small number of edges when I try to find a regular partition? Will I still be able to get this application, and will I get better bounds?
What is the question exactly?
I will say this in a second, more fully. Okay. The basic gist of the question is, what if I relax the definition of the regularity lemma by adding some more freedom? Can this application will this
remove so that it will be easier to have regular
exactly
pairs?
And I will say this like 3 more times in the next 5 minutes. Okay, so here is what I'm going to do in this talk. I'm going to show a new regularity lemma that does suffice to prove the graph removal lemma and also the hypergraph regularity lemma applications, which are maybe like 2 of the most hardcore, like hardest applications of the regularity lemma, for which we don't know much better bounds. And our new regularity lemma is going to have strictly better bound than Semmelweis regularity lemma. The bad news is that the bound that we get, we can actually prove is optimal. So it can be 2, and that bound is not exponential, say, like in the weak regularity lemma. So that's slightly bad. the ugly news, I say ugly because this is about the hypergraph regularity lemma, and the hypergraph regularity lemma is ugly. But you can actually use this lower bound to show, to give a tight lower bound also for hypergraph regularity. I will not mention this in this talk in detail, but I will just say that this lower bound proof was actually a key step for this result. But okay, moving on. So here's the name that we chose for our new regularity lemma. We call it the sparse regular approximation lemma, or SRAL for short. And I will explain the origin of the name next 20 minutes. So the question is as follows: what if I take this statement and now add here that we are allowed to modify delta fraction of the edges of the graph? Add or remove delta fraction of the edges of the graph, do we get, and we require the same. So we're going to define, for this talk, we're going to define this function with three parameters, epsilon, delta, p. So epsilon is going to be the same, like epsilon is going to be the regularity measure like before. Delta is going to be the fraction of the edges of the graph that we allow to modify. And p, we're going to need to be able to keep track of the density of the graph. So we'll add this p. And
we should think of delta as smaller than epsilon.
Let me just, so I'm saying exactly that. If delta is of order epsilon, then this is not actually stronger than Semeret's regularity lemma. Well, one way to see this is that if you take a graph and you modify some polynomial number of epsilon edges, then this doesn't change whether the graph is regular or not. Okay, you just need to look at the definition of a bipartite epsilon regular graph. So making order epsilon modifications is meaningless in this question. So the interesting regime is where delta is much larger than epsilon. Let's take delta to be much larger than epsilon, so a constant. So for the rest of the talk, I fix delta to be 1%. And I want to be able to find epsilon regular partitions, and the graph is of density p, and then let's just make things easy and fix epsilon to be some, I don't know, fixed power of p. Well, you can get so much more from our regularity lemma, but that will suffice for now. So we're fixing out of those three parameters, we're fixing epsilon to be some power of p, delta to be constant 1%. So we have only one parameter p. And so this is the bound that we want to study. So let me slightly be more formal and modify this statement of the regularity lemma to get the statement of SRAL with S. So the statement is as follows. So now there's no epsilon. I fix epsilon. So for every p and for every graph of density p, there exists an equipartitioned and a way to modify at most 1% of the number of edges of the graph.
So m of epsilon is replaced by
Right.
p.
Mm-hmm. So now this is the number of parts, the best possible number of parts that we can get, such that for all but epsilon, so this will be p to the 10, fraction of cluster pairs, we have that the induced bipartite graph is p to the 10 regular. Here's the statement. And the question is, what is the best possible value of S? Well, here is a very, very simple bound. You can just choose not to use the power to modify edges. So just apply the usual regularity lemma with epsilon, which is p to the 10, and you make 0 modifications, and the bound that you get is tau poly 1 over epsilon. In particular, SP is a well-defined function.
You can even remove the irregular pairs by...
Right, so this is exactly what I wanted to say now. Let's get back to the exercise that we said before, that we mentioned before. So what if I do that exactly? I remove all the edges between irregular pairs. Then the total number of edges that we remove is epsilon n squared, so p to the 10 n squared, which is the same as writing p to the 9, the number of edges of the graph. Right? So if you want to get rid of all irregular pairs, we can do this easily because we have the freedom to remove 1% of Pn squared. So this is basically for free. Okay, so we might as well replace this by 0. Okay, so there are no irregular pairs without loss of generality.
So P has to be more than 0.1, but P to the 9 has to be less than 0.
No. P can be arbitrary.
No, then it's trivial. You can
No, it's not trivial.
if you
Why?
remove 0.1 fraction of the edges, then you can just make the graph P empty.
For all
Come.
that's at least B.
No, it's 0.01 times the number of edges.
Oh,
Yeah.
That's important.
okay, sorry.
We are always talking about,
Right.
but take it for this because it's worth emphasizing. We're always removing not delta n squared edges, but delta
Right.
p n squared edges. Always a fraction of the edges of the graph. So this is always meaningful. Okay, so this is the setting. This is the question. The question is well, there are basically two questions here. What's the best bound you can get for S of P? Hopefully better than the trivial bound that Semmerit gives. And the second question, is this weaker statement suffice to prove applications?
This goes not a silly question, but delta is a constant polynomial in epsilon.
No. It's 1%. Delta is 1%. It's always 1%.
The observations say, yeah, right, 1 is 1%, is number 1, a polynomial function in epsilon.
I don't follow the question. You are referring to that?
No, the observation.
The observation?
Delta is smaller than poly epsilon, so it's not.
No.
That observation is if delta is smaller than poly epsilon.
Yeah.
tell me something. And no, 0.01 is not smaller than poly epsilon.
It does not add you power if delta was smaller than epsilon. It will not.
It's not interesting. This question that I'm asking is not interesting if delta is epsilon or something. It's not interesting. It has to be much larger than epsilon for this to be non-trivial. Otherwise, we're back to the. Otherwise, this statement is equivalent to Semmerit's regularity lemma. So, and we actually will show that this statement with delta, which is a constant function, is definitely not equivalent to Semmerit's regularity lemma. Okay, so. Again, I'm repeating now I'll rephrase things in almost an algorithmic way. You have the task underlying this SRAL. You are given a graph whose density is P, and you want to construct a, say, P to the 10 regular equipartition, and you have the freedom to remove or add 1% of the edges of the graph. Okay, I repeated it hopefully enough times. Here's the first question that I mentioned. Is it strong enough for those two applications? Like the first question is it strong enough to prove the hypergraph regularity and the removal lemma? Let's talk about applications. Does it apply the hypergraph regularity lemma? Yes. In fact, here is an interesting statement. It says that the following: if you can prove a bound for this SRAL, which is say exponential in 1 over P, like right, an exponential bound, just like the weak regularity lemma, or say double exponential or triple exponential bound. Then, when you prove the tree-graph regularity lemma, what you do there is you iterate the graph regularity lemma. In fact, instead of iterating the graph regularity lemma, we'll iterate SRAL. Of course, it introduces edge modifications, but it actually turns out not to matter for the proof of the tree-graph regularity lemma. And so what you get is an iterated version of the triple exponential function. And if you iterate the triple exponential function, you get a tower function. So much better than the known bounds of Wauser function. So
You didn't say this, but for hypergraph regularity, the bounds are much.
the bounds are a tower, or whose height is a tower, whose height is a tower. So the iterated version of the tower function. Here you will get an iterated version of the exponential function, of the triple exponential function, which is just tower. So much better than all possible bounds. Just a sec.
What is tower 1 over P?
So this means just like this is this means that we have 1 over P at the top of the tower. Okay, so if the tower is of height 1, this is just 2 to the 1 over P. So exponential, but yeah, good question. Right?
Yeah, so did you or someone prove some laws about allowed hypergraph regularity?
Yeah.
Yeah.
So now
But no one in the audience should maybe know that. So you're skipping ahead. My point is that this is a conditional statement. If we can prove this bound, then we will show later that no.
Thing is false.
This doesn't hold. Yeah.
Wait, why does it hold? Because the regularity lemma also has this.
No. So this is, forget about this for a second. This means a tower of a constant height.
Oh, I see.
So it's 5. Okay, and the proof is basically what I just said, modifying few edges when you iterate the graph regularity lemma in order to prove the tree graph regularity lemma doesn't change this potential function that for tree graph that you have there. It's not really important. What is important is just few works, like few means our notion of few, so if a constant function of the number of pn squared, the number of edges. Okay, which is kind of a lot, but this still works. And in fact, if you extend this iteratively for 4 uniform hypergraphs, 5 uniform hypergraphs, etc., and you will need to believe me that you actually can prove the removal lemma using this. I will talk about more about this for graphs in a second. And what you can get from this is this slide is not very important for the rest of the talk, so you're not supposed to understand it very, very deeply. But the point is that you can, if this assumption is true, if you can get a triple exponential upper bound for SREL, then you can get a tower type bound for what's known as the multidimensional Semiredis theorem, which is a statement about like multidimensional arithmetic progressions, which is a very general statement. And the best bounds that we have here are not even primitive recursive. So if we prove that the SREL has a triple exponential upper bound, then we have a proof of the first proof of say tower bound for the multidimensional Semiredis theorem, which would be big news. Okay, that's it about hypergraphs.
So the best lower bounds we know for both these problems that is tower?
No.
So we'll talk about lower bounds soon. Okay. So, but I will want to focus on the removal lemma. That's the more interesting thing here, I think. So again, here's the statement of the triangle removal lemma. It says that if your graph is epsilon far from being triangle free, then the total number of triangles is large. Does SREL imply the removal lemma? Yes. In fact, we get essentially very clean bounds. So the same bound that you get, if you take S of P and you plug in instead of P epsilon is now the parameter for the removal lemma. S of P gives you, or S of epsilon essentially gives you the immediate bound, the same bound for the removal lemma.
So this greatly improves the Fox result.
I will talk about this. Right now we don't know this. Right now we don't know what's the bound on what's the best. If we can get S to be better than Semiredis bound. Eventually, yes. Okay. Okay. So let me try to prove this. Let me try to show how SREL implies the removal lemma. It's a cute proof. First, I will need what's known as the counting lemma. The counting lemma is a very basic notion in this area of regularity lemmas. It's what makes the regularity lemma useful. It's what makes the compressed graph, the compressed model, useful. So what does it mean? What does it say precisely? The setting is as follows. You have a tripartite graph. We're actually giving the counting lemma for triangles. So we have a tripartite graph, m vertices in each vertex class. And let's assume that all 3 bipartite graphs are epsilon regular. And their densities are alpha, beta, and gamma. Then it turns out that the total number of triangles is what you would expect from a random graph with some error. So alpha, beta, gamma plus minus epsilon times m cubed. Okay, so if all 3 bipartite graphs are quasi-random, then basically the tripartite graph is quasi-random. That's the intuition. And so why is this so important in general for the regularity lemma? It's because it says that if you find a triangle in the compressed graph, then this translates, and I will show this in detail, this translates into many triangles, this many triangles in the original graph. It allows you to count subgraphs, in this case count triangles, in the original graph by counting them in the compressed graph. Okay, but we have a different regularity lemma, so we will actually need a new version of the counting lemma. We call it the approximate counting lemma. So here the setting is as follows. As before, we are going to assume that in our tripartite graph, all 3 bipartite graphs are epsilon regular. But also we have this restriction. We have some set of red edges, of forbidden edges. So forbidden in the sense that now we want to show that there are many triangles, say. We are not allowed, our triangles are not allowed to use any of the edge, or any of the forbidden edges. Why? I mean, intuitively, why? Where is it coming from, this forbidden thing?
These are the delta function you
Exactly. So when I...
on average overall. Yeah.
Exactly. So the thing is that when you apply the SRL, you are going to modify edges. In particular, you are going to add edges. But you want to count triangles in the original graph. And if you find triangles that use edges that were added by SRL, then they are not going to be there in the original graph. So we actually have some amount, and we need to quantify some amount of forbidden edges that we are not allowed to use. The question is, can we still deduce, say, a lower bound? Can we still deduce that the number of triangles is, I don't know, at least 1/2, some constant fractions, or a fraction of what you would expect from a random graph, alpha, beta, gamma, m cubed? So obviously the answer is yes if the number of forbidden edges is very, very small. Why? Because if this is the number of edges, of forbidden edges, epsilon cubed m squared, then how many triangles use one of the forbidden edges? At most m times that, right? So that would be m cubed. And so the thing is that if alpha, beta, gamma are larger than epsilon, then the usual counting lemma gives you tons of triangles, and the forbidden edges forbid a very small number of triangles. So who cares? But that actually this is not the case we need to handle. We need to handle the case where you have many more forbidden edges, and here is the statement of the approximate counting lemma. If the number of forbidden edges is at most a fraction, so 1/6, like I said, some constant fraction of the edges in each bipartite graph. So in this bipartite graph, the alpha density bipartite graph, we can have at most 1/6 alpha m squared forbidden edges, and similarly for this bipartite graph and this bipartite, each of them separately, then we have a counting lemma, we have this statement. We can show that the number of triangles is at least, say, 1/2 of the number you expect here.
How do you prove this?
So here's the idea. The idea is in fact the counting lemma actually gives you something stronger. So not only, no, so here's the usual, I'm going back to the usual counting lemma. It gives you something about the total number of triangles. In fact, it gives you something stronger. It gives you that for almost every edge that you fix, the number of triangles that use that edge is what you would expect from a random graph. Okay, so now if you use that, well, that's enough already, because, well, consider one of the forbidden edges in the alpha density bipartite graph. This is the upper bound of the number of forbidden edges there. Well, we know that for almost all of them, they rely on the correct number of triangles, which is beta, gamma, m. And so in total, the number of triangles forbidden by those forbidden edges in the alpha graph is the product, roughly the product, 1/6 alpha m squared times beta, gamma, m. Okay, so that's 1/6 of the total number of triangles in general. Okay, but this, we now need to repeat this argument for every forbidden edge in the beta subgraph and also in the gamma bipartite graph. Okay, there might be repetitions, but fine. And so you need to multiply this by 3, so you still get that you only forbid 1/2 of the triangles that you find, so at least 1/2 of the triangles that you find survive. Okay, so this is the idea in the approximate counting lemma. Now let me show you how to use this approximating counting lemma and the SRL to actually prove the removal lemma. Okay, and the proof is going to be a nice twist on the usual proof of the removal lemma using Semmered's regularity lemma. So those who know that proof, this is going to be familiar with some twist, and those who don't know, then are getting a treat. Okay, the proof is kind of natural, but the first step is crucial, and you will see why in a second, in 5 minutes. First, we're going to assume that the graph, so again, we're trying to prove the removal lemma. I remind you the statement, for every graph that is epsilon far from being triangle free, there are many triangles there. Epsilon is the distance from being triangle free. In fact, we can assume that our graph is not of density 1/2 or 1/3. It is actually of density epsilon, and it's epsilon over 3 far from being triangle free. So why is that? So take your graph, which is epsilon far from being triangle free. In particular, it has a triangle. So take a triangle outside of the graph. Now it might have not more triangles. So you add them, and the point is that at each step you're going to want to find a triangle which is mutually edge disjoint with the rest of them. So you're going to have to find a maximal collection of edge disjoint triangles in your graph. And so if you actually think about it, what you get here, once you're done, you get a collection of edge disjoint triangles. The total number of edges in your triangles is going to be epsilon n squared. And why is it epsilon over 3?
Epsilon n squared, epsilon. Total number of edges in our.
The total number of edges is going to be epsilon n squared.
In the disjoint.
We're just taking disjoint triangles.
In the disjoint triangles, you will have linear number of edges.
No, edge disjoint.
Yeah. When I say disjoint, I always mean edge disjoint. So of course they can share a vertex, but not an edge. So each edge lies on exactly one triangle. Why is it still epsilon over 3 far? Not epsilon, but epsilon over 3 far from being triangle free? Because in order to get rid of all triangles, you have to remove at least one edge from each triangle, right? There's no overlap between the triangles. Okay, so this small trick it basically didn't change the how far our graph is from being triangle free, but it did reduce the number of edges, and this will be important. But let's move on. Okay, so here's what you do: you apply the sparse regular approximation lemma, where the parameter is obviously p, the density of the graph. Now the density is epsilon. Okay, so you apply the sparse regularity lemma with p equals epsilon to get this modified graph G prime. So G prime was obtained from G by modifying 1% of the edges there. And once you have this graph, we're going to now clean it. So we're going to remove all the edges that lie within clusters between irregular pairs. If you have Vi and Vj, and we have no guarantee on the bipartite graph there, where it's either regular or not, we're going to remove the edges. Or as we said before, you can actually assume there are none, no irregular pairs. And importantly, we are going to remove all edges in bipartite graphs, so between Vi and Vj, whose density is small, smaller than some fraction of epsilon. So this is like a cleaning phase, and if you keep track, you see that the total number of modifications, so the number of removals that you made here plus the 1% of modifications that SRL did was at most, say, 1 over 4 epsilon n squared. Okay.
So here you use the fact that at least one over epsilon partition part.
Yeah, so it will be important. Yes, thanks. Okay, but the original graph is epsilon over 3 far from being triangle free. Okay, you need to remove epsilon over 3 n squared edges to get rid of all triangles. So in this clean graph G double prime, they will remain triangles. So at least one triangle will survive there. Okay, what can we say about this triangle? Due to the clearing phase, we can actually say a few things. First of all, we know that the vertices of this triangle lie in distinct clusters, right? Because we removed all the edges within clusters. Also, we know that all these three bipartite graphs are regular, epsilon regular. There are no irregular pairs, so if there are, we remove them. And we know that all three densities, alpha, beta, gamma, all of them are of density at least epsilon over 8, because those that are of a smaller density will erase. So we know that we are in this setting, but this is exactly the setting which allows us to apply the counting lemma. We apply the counting lemma. How many triangles do we get? Roughly alpha, beta, gamma, m cubed. M is the number of vertices in a cluster. Alpha, beta, gamma are all at least omega of epsilon. So what we get is roughly omega epsilon cubed, m cubed triangles in this clean graph G prime. Just a sec. And the thing is that what is m? M is the number of vertices in a cluster. but remember that the partition is an equatable partition. So M is actually equal to n over the number of parts, n over tower, right? So this gives you n cubed over m cubed or s cubed times epsilon cubed. And so this is well, the epsilon barely matters here, because at the bottom we have like a tower function. So this tower function is this is where you get the bound for m, right? You get n cubed triangles divided by some function of epsilon, and this function of epsilon is basically m of epsilon or s of p. But the thing is, as I said before, this is not enough, because we removed tons of edges. We removed one fraction of the total number of edges. So epsilon, like n cubed over a tower number or s of p is negligible compared to the number of edges that we modified. So it very well might be that all of these triangles that we found use edges that were modified by SRL. So they're not actually, they are in G prime, sure, in G double prime, but they are not in G. So we have nothing. Again, this is because we use the sparse regular approximation lemma and not the usual regularity lemma. If you did use the regular approximation, the usual regularity lemma, sorry, then this is the end of the proof. So hopefully now we can apply the approximate counting lemma and get this many triangles, not in G double prime, but actually in G. But we can't apply the approximate counting lemma simply because we're not in the setting. Our setting requires that the number of forbidden edges, or the number of modified edges, would be bounded, so at most 1/6 in each bipartite graph.
On these three pairs.
Exactly, right? Which is why, right, we might have tons of forbidden edges, which is why we're going to augment the cleaning phase. So in addition to these removals, we're going to also remove all the edges between pairs Vi, Vj, where the number of modifications that SRL made was greater than 1/6 of the edges there. Of course, different pairs have different number of edges, but it's relative to the number of edges there. And if you think about it, that increases the number of edge modifications that you make by some omega of the number of edges. And here's the important bit: the number of edges, by our trick at the beginning, is only epsilon, n squared. So in total, the number of modifications is less than, well, not epsilon over 4 n squared, but epsilon over 3 n squared. But that's still enough, because we are epsilon over 3 far from being triangle free. And so so we can still do that. We can still deduce that the triangle survives. And now we apply the approximate counting lemma, so we get many triangles. This many triangles, basically the same number of triangles with 1/2 here, say, that do not use forbidden edges, meaning that these are triangles, genuine triangles in G. Okay, and this is it.
So this initial process of taking edge disjoint triangles, usually you don't need it in the
right. So that's a good point. So you actually don't need the first step, because we needed the first step only for counting the number of modifications after we did this extra trick. The original proof using that uses Semmelweis regularity lemma doesn't need that. You can do that, but doesn't need that, and you don't need this additional cleaning phase, and you apply the usual counting lemma, and that's it. Okay.
You can't say this proof without doing that phase, with some finding an average triangle.
I think you can also, by the way, do like the usual proof of the removal lemma without removing, by just rephrasing things in some averaging way. Yeah. It's not. I think it's just nice. Oh yeah.
Well, you only need one triple of parts in order to get the bound you want.
That's a very important point. Notice that the reason we get such bad bounds in the removal lemma, this proof of the removal lemma, is that we only get our triangles from just 3 clusters out of the many triangles, out of the many clusters there are. So just a tiny portion of the graph is the one that we extract many triangles from. We have no way to basically argue about what happens in total.
But even if you did, it will change epsilon squared to epsilon cubed to
No, it's
epsilon squared or something.
no. The epsilon here doesn't matter. What matters here is that you have m rather than m.
But
Sorry, m rather than n.
I know, but m is roughly n over s.
Right.
Yeah, so you would get, I mean, even if you found the linear number, it wouldn't change much.
One head.
A constant fraction of order.
Most triangles.
Most triples in the skeleton.
If you got most triples, but
Right.
this kind of argument may give you just maybe disjoint sets. I mean,
I'm pretty sure that this type of argument can't give you something much better than a single triple of clusters. Much more triangles than what you find there in a way. Okay. So, we see that some very important applications of the usual regularity lemma can be deduced from SRL. Let's see what can we say about S of P. So we saw that SRL is strong enough for these applications. Does it have a bound which is better than Semmered's bound? So if your graph is dense, then you might as well not remove 1% of the 1% of Pn squared. Just remove 1% of n squared, because if your graph is of constant density, then you get what you can call the dense regular approximation lemma as opposed to the sparse regular approximation lemma. So this was the original regular approximation lemma that people proved, but they had other intentions.
So it means delta times n squared instead of delta times p.
Exactly.
Yeah.
The original motivation was not to get better bounds compared to Semmered's regularity lemma, but to get better guarantee, stronger guarantee. So now they used it to get they use it to get epsilon regularity, where epsilon goes down with the number of parts. Never mind why, but they use it to get a stronger guarantee. They couldn't care less about. They didn't even hope. They didn't even dream to think that you can actually improve Semmered's bounds. So this was originally works by Lovas-Segedi and Redl-Schacht. Qualitative results, so they didn't say anything about the bounds, and Conan and Fox actually were interested about did give an argument that gave bounds, but these bounds in our notation, this is the bound that they give. So it's a tower of height polynomial in 1 over p, where you have 1 over epsilon at the top. So if p is 1/2, say, is an absolute constant, then this is a very nice bound. You get a tower of constant height with 1 over epsilon at the top. But for the setting that we need, where the density of the graph is some parameter p, so the bound that I give for S of p is still tower polynomial of 1 over p, unfortunately. So the result doesn't give anything better than Semmered's bound. It does give a stronger guarantee. By the way, also our proof also gives a stronger guarantee, but our proof will actually give better bounds. Okay. Here's our proof of the SRL, or this is the bound that we get. So it's still unfortunately tower type bound, but the height of the tower is not 1 over p, but logarithmic in 1 over p. So you might be disappointed that it's still a tower bound, but you can actually rephrase things and say, well, it's a huge improvement over the original, right? It's much better than exponential improvement, right? It's all about how you put things. Anyway, and the immediate corollary of this application to the removal lemma is that rem of epsilon, as we said, is our proofs show that this is the bound that we get. So you get a tower of logarithmic height bound. And in fact, we were late by a few years because Jacob Fox famously proved the same bound for the removal lemma. The reason why Jacob Fox's result was very interesting, despite the bound being still a tower type, is that people wondered whether the removal lemma is actually equivalent in strength, in some sense, to the Semmered's regularity lemma. Because in many other applications, we have much better bounds, exponential bounds or whatever. For the removal lemma, we are still not able to find better bounds than what Semmered gives us. And Jacob used some ad hoc method to actually show a separation there. So the removal lemma is something different than Semmered's regularity lemma. What we showed is that not really. So if you actually allow modifications in your definition of so semi-ready was too restrictive. If you allow modifying 1% of the edges, then you can again recover this bound. So it still might be the case that the removal lemma is equivalent to the regularity lemma, except not semi-ready regularity lemma, but the SREL. And another benefit is that Jacob's proof was rather ad hoc, and ours is like more systematic. You have like an appropriately defined regularity lemma, and then you just do this, and you just do this proof that we did before with this counting triangles and the approximate counting lemma. The usual thing with a twist.
Well, I don't know if I would call it exactly ad hoc. I think in all these proofs, the proof proceeds by finding a good progress measure on modifying the graph towards building the partition. In
Right.
the original one, you use the square norm, and in Jacob Force, for the removal lemma, you use an entropy.
So that's
So I don't know if I would call it ad hoc.
that's not the only difference. No, this actually we will also use the entropy potential function.
Yeah, I know.
So that's not the issue. The issue that he has it's that in the original proof he defines this notion of shattering and all kinds of notions, and if you so it looks like a series of lemmas that are not easily explained.
It's higher level because it's a more general.
That's all I'm saying.
Implies it, but
That's
definitely.
That's all I'm saying. Yeah, didn't mean anything else.
So both
Yeah.
of these are towers of big O of log of 1 epsilon, but are they kind of the same number?
Is the big O hiding the same constant? Is that what you? Yes, I think it's like maybe by a factor of 2 or something.
Yeah, but factor of 2 is a big thing.
But you can actually be more careful with the analysis. I'm pretty sure you get exactly the same thing. I think that I actually think that the O here hides a constant which is 1. If you properly analyze things. Otherwise, 2.
It's very interesting if they are equivalent. It's not people try to.
The removal lemma and SREL.
Yeah.
Of course, that's a major open question. So an open question, a natural open question, an additional open question is find more applications of SREL. So we were able to reprove a Fox result using SREL. Can we actually prove other results? Okay.
Is there a similar log saving, or not log saving, I mean this similar improvement in hypergraph removal lemmas or anything?
So that's also an open question. So no one sat down to do that. I suspect, including me, I admit. So I suspect that yes, for the hypergraph removal lemma, for the trigraph removal lemma, you can get a wowzer of log 1 over epsilon rather than 1 over epsilon. But you need to sit down and do that. Okay.
Also ask, so back to this slide. So about this equivalence, so it seems that this regularity lemma, you can extract so much structure, even more than triangles. And triangle removal just talked about triangles. So what's the intuition for them to be equivalent? Like,
I actually don't suspect that they are equivalent. The question that people ask is, do you get this roughly the same bounds? I don't think that anyone necessarily have like a clear correspondence between the structure here and triangles there.
But it's a really good question. In the other cases, other structures where you look at pseudo-randomness, and the answer is yes. So you may know about pseudo-random graphs, quasi-random graphs. And there, again, for dense graphs, the following 2 properties are equivalent. That the number of, let's say the graph has half n squared, or half the total number of edges. It's like g and half, but it's a fixed graph.
So the following 2 properties are equivalent. One is that the count of C4 as cycles of X4 is what we expect up to epsilon. And the other is that for every fixed size subgraph, the count is what we expect up to epsilon. And then you guys, so the point is good potential.
So there is universal. It's there for relatively simple reason of it's related to the eigenvalue of the graph. So it's Anyway, it doesn't matter.
I will say one thing in this.
Sometimes magic like this happens.
But okay, we say magic, but let's say it more systematically. So we can talk about not just the triangle removal lemma, but the graph removal lemma for any fixed graph that you want instead of triangle. If this graph is C4 or any bipartite graph, then it turns out that the removal lemma has polynomial bounds. Period. This is easy. So if the removal lemma for bipartite graphs is easy, that's not the question. The question is about non-bipartite graphs, in particular the simplest case being a triangle. Okay?
Any lower bound known for the removal lemma?
Yeah,
Epsilon to the log 1 over epsilon.
That's it.
yeah, I mentioned this at the beginning. Slightly super polynomial, but yeah.
So the methods of Fox and this are not known to extend to graphs of the triangles. They are.
That's how they're not.
They, like, we have upper bounds for removal lemma for graphs that are bigger than just triangles.
Right. No, so I mentioned everything for triangles, but it actually holds for any
Okay, that's
fixed
what I
graph.
thought. It works
Yeah.
for everything then. Okay.
Yeah.
It works for all graphs.
And of course, the bounds, like the constant here would depend on the size of this bar.
You have a tower of log 1 over epsilon for every fixed graph.
Correct. Yeah.
So for all these triangle removal lemmas, do people believe towers are necessary, or?
That's a good question. I know that at least a few people believe that the result should be actually closer to the lower bound.
Well,
But everyone is just guessing. We actually have no intuition here even. And very clear. Yeah. It's maybe like the largest gap that I know in an open problem between the lower and upper bound. Okay, what about the lower bound, not for the removal lemma, but for SRAL? So we show that up to the constant in following the log, our upper bound is actually optimal. In particular, if you remember this application that I mentioned that said if you can prove SRAL, if you can show that S of P is at most double, triple exponential, then you get amazing results. Well, you don't. You don't get amazing results, sorry. But the thing is, okay, so that might seem not impressive. So fine, so this approach for example, to prove the hypergraph regularity lemma doesn't give you better bounds. It's still tower bounds, and if you iterate, so right, it's tower of log, but if you iterate this to prove the trigger regularity lemma, this log doesn't really matter. Still, the bound that you will get is still going to be Wowzer bound. And so you might say, well, fine, so this approach to proving hypergraph regularity lemma using SRAL instead of the usual regularity lemma is not working. Thing is that in some sense it's the only approach in some vague sense. So more formally, this proof, or someone that proved that a lower bound proof that built on that actually can show, or this was a key step in proving that a lower bound, a tight lower bound for the hypergraph regularity lemma, which was an open question in this area. But so, which is why this lower bound is interesting, not only if you care about SRAL, but also if you care about the hypergraph regularity lemma. Okay, so no more about hypergraphs. Okay, so let's take a short break, and then I'll sketch the proofs of the upper and the lower bounds. Okay. Oh, so we're talking about the upper bound. What are the main ideas in order to prove this SRAL regularity lemma? So again, here's the definition of SRAL. In case you forgot, you are given a graph of density P. You want to find an epsilon regular partition. Epsilon is some power of P, and you have the freedom to modify 1% of the edges. So we are going to use. So the proof is going to iterate what's known as the weak regularity lemma, or Friis-Kahn regularity lemma, which I've mentioned before. Let me just give the formal definition now. It's an interesting lemma. It says that. Oh, first, before the lemma, here's the definition of a partition which is weak epsilon regular. Here the requirement is that for every two large sets, the density between them is what you would expect based on the compressed graph. So let me try to compare this to the usual regularity lemma. In both cases, you find some partition of your graph. But in semi-reduced regularity lemma, you have a local guarantee. So you know that every or almost every pair, if you look at on this bipartite graph here, it's quasi-random. What the weak regularity lemma gives you is a guarantee which is like global. So if you take large subsets of the whole graph, so 5% here, 7% there, 35% here. Yeah. Here's no, it's not the best color. Here is a subset. Here is a subset. Here is a subset.
This is all one subset.
This is S. S, the intersection of S with V1, the intersection of S with V2, the intersection of S with V3, and let's say this is T. T can also, by the way, contain elements there. The point is that S and T are two linear, essentially linear, two large subsets of your graph, and a weak regular partition guarantees that the number of edges or the density between those two large subsets is what you would expect based on the densities between the VIVJs. Okay, so the difference is clear why this is a weaker notion. The regularity lemma, if you have a regular partition, then in particular you get this guarantee. And here is the Friskanen statement, the regularity lemma. It says that every graph is an epsilon regular partition whose order is, as I said before, exponential in 1 over epsilon. Sorry?
Yeah, it's tight. Yes.
Yeah, it is tight, yeah.
It's tight.
In fact,
the proof is much simpler than the.
And also, not only is it tight, people actually know the correct exponent in the poly here. And in fact, slightly something a bit stronger than that. If you fix any initial partition, P naught, and you want to find an epsilon, a weak epsilon regular partition that refines this P naught, refines mean that it is obtained from P naught by further dividing each part. So you can actually get it with the same part. Okay. So I will need to define a notion of distance between two partitions, between namely a partition and a refinement of it. So let Q be a refinement of P. Okay, let me just have a generic drawing of that.
Maybe before you say something very high level, that all proofs of all regularity lemmas proceed by starting from some partition, and if it's not regular, you refine it and you improve on how close you get to being epsilon
exactly.
or epsilon alpha.
So I give the proof and this
I know, but it's high level thing. I mean, this refinement of partitions is the only way we know how to prove regularity.
Right. And by the way, this explains why you get this for free. Basically, because the proof of the weak regularity lemma is like the proof of any regularity lemma. Basically, is basically iterating one step, and this one step is you are given a partition, you find a refinement of it, which is better in some sense. So you can just start the process from whatever partition that you want. Okay, so we have a partition P. These are the clusters of P, and we have a refinement of it. So each cluster of P is further partitioned by Q. Okay, so Q is blue, P is white. Okay. Here's the normalized L1 distance between those two partitions. So we're going over all parts in Q. So all pairs of parts. So every, say, this part and this part, two blue parts. And we are asking what is the density between them in the graph compared to the density of their parents in P. So compared to the density between those two larger clusters. And so we count the discrepancy between them, and we just sum, or rather more conveniently average this over all parts of Q.
So probably it's good to relate this definition to the definition of an epsilon regular pair. You wanted that every large subset of the two parts will be like the parent one. There was no parent, no partition, but it was the same sense. So basically, if you don't have something like that, this is what you want to improve or minimize this.
Right. So the obvious observation here is that if this bipartite graph is already epsilon regular, then definitely it's the case that for any subset here and subset there, in particular parts of Q, but any subset here and subset there, the density between them is going to be equal to the density of the parents plus minus epsilon. Okay?
But only if the subsets are large enough, right?
Yeah.
Of course.
They will be large.
Yeah. Okay.
So maybe even one more comment.
Yeah.
The original proof of lemma is just the following. You have a partition P, it's not good enough, it's not epsilon regular, there must be some subset in one part, some other subset in another part which is not. you refine just making these parts of whatever arbitrary partition Q. And that's the only thing you do.
Right.
And then you iterate. Somehow this process converted.
Right, but what you just described basically gives you an exponential, bound.
No bound, just the idea.
Right. Why you get tower bounds in this proof is because you have to do the same multiple times, so you have to take the common refinements of many partitions. This will be clear later.
This is the main difference. In fact, what you said, the main difference between semi-disk proof and Fritz-Cannon proof.
Right.
They
Whether we
need to be consistent.
Right. So in Fritz-Cannon, basically, you don't care about taking common refinements of multiple partitions. So in each step, you double the number of parts rather than take an exponential number of parts for the refinements. Okay. We will talk about the lower bounds and everything will be hopefully clear. So here's a lemma by Conan and Fox. Here's the statement. So it's a statement about a single bipartite graph. So fix V and V, two big clusters, two clusters of P. So we're only talking about the bipartite graph between them. And suppose that the partition induced by Q on them, so the partition into the blue parts, is weak epsilon regular, in the sense that we just talked about. Then it turns out that the bipartite graph between the two clusters can be made epsilon regular by making a small number of modifications. This number is basically given by the normalized L1 distance. It's basically you take the differences, the average difference of a density between two clusters of U and the original density. Why is that? Where is this coming from? The intuition is kind of clear. Or specifically, what is the algorithm? How do you make this bipartite graph epsilon regular? The thing is, between those two pairs, maybe the density is 37%. But in the original, in the entire bipartite graph, the density is 30%. So what you're going to do is you're going to randomly remove edges in this small bipartite graph to make the density go down to 30%. Okay, and you do this for all the pairs. What is the total number of the expected total number of modifications that you make this way? That's basically the L1 distance between this partition and the trivial partition into two parts, so which has one density, 30%.
Independent of random. By randomly, you mean randomly or arbitrarily?
Randomly, truly random. It's important it will be independently uniformly.
You don't want to ruin other regularity properties.
I see. But this distance bound happened whether it was random or not, right? You're going to remove 7% of the edges. So now then the distance.
Yeah, but the question, how do you remove? You need to remove this many edges, but also make sure that it's going to be epsilon regular.
Okay, and you haven't described that.
Right. I'm not actually going to talk about the proof. I'll just give you an intuition why after equating all the densities, now after these modifications, all those densities are going to be basically 30%. Why does this turn weak regularity to actual regularity of this bipartite graph? Well, it's kind of easy, because this is the definition. This is the definition of a weak epsilon regular partition. And now, so these are not, in our case, these are U and U prime, the densities of the blue parts. And all these densities are the same, 30%, so take it out of the sum. But so now the sum is actually 1. Okay, if you think about it. So the density, it just says that the density between any two subsets of this bipartite graph is just 30% plus minus epsilon. In short, if you have a weak regular partition where all the densities are the same, then by definition you have an irregular bipartite graph. Right? Okay, so this is the idea here.
Also, sorry, so within V and V prime, did you do something else, or just across V to V prime?
Yeah, I couldn't care less what happens in the edges within a cluster. Yeah, I never care about that. Yeah, and here is a corollary of that. Now let's get back to the original graph, where there are not many clusters of P, not just two. If it so happens that when you induced the blue partition Q onto every pair of clusters via V prime, you get a weak epsilon regular partition, so you can apply these modifications. Then the implication is that P can be made epsilon regular by making L1 times n squared edge modifications. The proof is trivial, right? You just apply that for every bipartite graph and sum everything together, and what you get is the normalized L1 distance if you average over, or sum or average over all this. Okay, so basically what we need, we want the number of modifications would be 1% of the number of edges. So we want the L1 to be bounded by 1% of P, right? So how can we guarantee this? So what we need is what's called the defect inequality. I'll explain in a second, for graphs which are sparse in the sense that the density is not a fixed constant. We need to control this L1 distance. So there's a lemma. Suppose that you have a graph of density P, and we are in this setting, you have partition P refined by partition Q, and we're going to define, so we have this sequence of numbers. So every partition P determines a sequence of numbers, just the densities between all possible pairs. Take the entropy of that, or minus the entropy, it doesn't really matter. Then it turns out, and this is what's called the defect inequality, if the L1 distance between P and Q is large, if the densities in Q are don't very much agree with the densities of their parents in P, then the difference between the entropies of Q and P is also large. Everything relative to P, and this is important. So something like that, which gives you, like if you can deduce that the distance between partitions is large, if you can deduce from that a simple difference between two univariate functions of partitions is large, you can call this a defect inequality if you want. I'll use it in a second. I'll just say a word about the proof. The proof uses Pinsker's inequality from information theory, which what it says is that it bounds the DKL distance, if you don't know what it is, that's fine, by the statistical distance, using the statistical distance of two distributions. Here we don't quite have distributions, we need to properly do things, but you need to trust me that it actually follows. And we also need these facts about this entropy function. First, by convexity, the entropy of a refinement is at least as large as the entropy of the parent. And also, and this is important, the entropy, or if you want the minus entropy, but the minus of that would be entropy, but never mind. It's bounded above by 0, but...
I mean, the two lines are inconsistent, I think, because h of q is at least h of p when they are positive.
H of... No. The function h is negative. It's always negative. It starts. It's like.
The entropy of q is larger. I mean, just.
You start from something small and you go up.
That's right. When it's positive.
What is positive?
H of p. H of p is negative or
negative. Negative. Everything is negative here.
But then it should be that h of q is smaller than h of p.
It starts off at e log p and goes up to 0. That's what you're...
Yeah. P. Let's be clear. Ln p is a negative number. Okay.
Yeah,
so you start. Yeah. So
then the first row, the inequality should be reversed.
Why? So what's wrong with what Swastik said? You start with p ln p, which is a negative number, and then you keep increasing this until you reach, say, 0.
Because it seems to me, I mean, if you have more parts, then the entropy as a positive quantity is larger. What happens.
More parts?
Exactly the entropy of the random variable, which is the uniform.
Yeah, it's
part. This is the entropy
of densities of things. You can't quite say that if you have a bigger partition, then you have something. But what is important to remember here is that the range, forget about the sign of this function h, the range in which h lives, the size of it is p ln 1 over p, right? The difference between 0 and... So okay? And this will be important. Okay. So it's not... h is not between 0 and minus 1, say. It's between 0 and something which is larger than minus 1. Okay. So here's the sketch of the proof, follows by this corollary that we mentioned before, and this sparse defect inequality. So you iterate the weak regularity lemma as follows. So at each step you start with an arbitrary partition, and then at each step you take the current partition pi and you apply the weak regularity lemma starting from that partition. So you get a refinement of that partition, and we want a weak epsilon regular partition where epsilon is this number. So p to the 10 divided by, and this is important, the number of parts in the original partition. Like in the current partition, sorry. And the bound that you get from Friskanen's result is that the number of parts in pi plus 1 is exponential in number of parts in pi. So if you apply this many times, you get a bound which is 2 to the 2 to the 2 to the 2, roughly, where the height of the tower is the number of iterations, is r. And we're going to repeat this until we get to a favorable, to the case that we want. We would want that the L1 distance between the current partition and the previous one would be bounded by 1% of p. So we're going to continue until this happens. I will bound the number of iterations that we have to make r in a second, but notice that once we're done, we have the partition pr plus 1 and pr. PR is the big partition, like into big clusters, and PR plus 1 is a refinement into the blue parts. Because of this choice of epsilon of regularity here, we get that if you induce to every bipartite graph, to every two clusters, the induced partition there is not this regular p to the 10 over pi, but p to the 10. It's not too hard to see that. But now we are in the setting of this corollary that I mentioned, and so because between every two pair of clusters you have a weak regular partition, and so it can be made p to the 10 regular by modifying only 1% of the edges by this assumption that these two partitions are close in L1 distance. And the only thing you need to show is that the number of iterations is small. Well, by the sparse defect inequality, since in each part, let's go back to the defect inequality. We know that as long as this happens, as long as we are not done with the process, as long as the current partition and the previous one are far apart in terms of the densities, then also the difference between the entropies is large. Some function is some constant times p. So each step increases p by some constant c. So you have cp plus 2cp, 3cp, etc. But how many times can you add p to age? Because of this range, you can add ln 1 over p. So the number of times you can apply this, a number of times that the entropy can increase by that much, is just ln 1 over p. Okay, so hence the number of iterations is most log 1 over p, and which completes the proof because the number of parts in PR is the tower of the number of iterations, so tower of log 1 over p. That's the entire proof. Okay, that's the take-home message from this upper bound proof is that you find two closed weak regular partitions, and you can use the refinement, like the smaller, like the partition into smaller parts. You can use it to see where are the modifications that you need to be making. Right? Whenever you see 37% rather than 30%, you just change there 7% of the edge. Okay, you remove. So this gives you like a template what you need to modify in order to get an actual regular partition.
So you don't see a particular reason why some other trick will not get it down to log 1 over.
What is the low bound?
I will talk about the low bound showing that you can't.
Oh, sorry, for this, I was thinking about the application to...
applications is something very different.
Very good, yeah. This is
No, but the bound here is tight, lower bound proof.
Yeah, but that's the question.
Yeah.
So how many total edges are you modifying in that? Can you just go over it?
0.1 p n squared.
Okay, so in each step you're modifying how many?
So I'm not modifying
Only at the end.
only at the end. I iterate until I find two close partition, then I do all the modifications.
Okay, I see. Okay, I'm sorry, I was confused about that.
Okay, so this is all about the upper bound question.
So was this whole proof like an efficient algorithm also? Like you can actually construct it?
Possibly. Yeah, it seems.
There's no statement in your papers about, because for semi-regular, there is polynomial time algorithm. You didn't even worry about this. making this statement.
If we had like a concrete application that required like a computational application that required an efficient algorithm, then that would be sufficient motivation. We just
There are applications too.
of SRAM.
Well, yeah, okay, so
But yeah, I mean, sure, it would be nice to adapt the proof, the algorithmic version, the algorithmic proof of the Semmelweis regularity lemma to this version. I bet this can be done.
yeah. For example, finding a triangle in sorry, I see it doesn't. Okay, doesn't matter.
So the weak regularity is algorithmic.
Yeah.
Yeah, it's very simple. I mean, that's
So you
very.
can keep doing this.
Yeah, it seems.
So why is this not algorithmic? You just keep doing.
Probabilistic though, but I think this, yeah, I think it does. I think it does, yeah. Okay.
Actually, I didn't see where you use the fact that you randomly.
Oh, so in this proof of Colon-Fox, which I didn't give fully.
Oh, right, okay.
But you may ruin the regularity that was there if you don't do it randomly.
Right, good. I see. Right, you can just make a bipartite.
Yeah.
Right.
It's actually quite subtle. I actually had to work hard. Like, okay, I won't go into this detail, but it's a non-trivial proof, and there's something interesting there when you actually analyze like what happens exactly when you do these random modifications. But anyway, moving on to the lower bound. I have 20 minutes. Hopefully, this will be enough to give some ideas. Okay. Okay, skip that. No time for that. This slide just basically says that since the lower bound is tight, it makes sense. It's like a reverse engineering of some upper bound. So it's kind of obvious. So it's not very obvious from our proof of the upper bound, but there is an alternative proof which we didn't write because I think it would be less nice. From which it kind of easy to see why our lower bound. So our lower bound construction is meant to be like reverse engineering made to be hard for this proof. But I won't talk about that. Okay, so here's the construction. Okay, switch.
The construction of a graph with.
Yeah, the construction. So let's. I'll just say that I'm done with the presentation basically. So. Or maybe no. I'll stick with the presentations for now. I just write on the board anyway. And let me know if you have issues seeing what's written on the board. I'm going to describe the construction, the property that what we want to prove. We want to show that for this graph that we construct, no matter how you modify it in 1% of its edges, still any regular partition of it, any epsilon regular partition where epsilon is p to the 10 or whatever, has to be large. Large being tau of log 1 over p. So here's roughly the construction. First, I'll define an operation on graphs, what I'll call a modified blow-up of a graph. So you start with some arbitrary graph, and here's what you do. First of all, you take a blow-up in the sense that you replace every vertex by k new vertices, by a new subset of vertices. And whenever there was an edge, so suppose here there was an edge in the original graph, first of all you blow up, so you replace this by a complete bipartite graph. Okay, but then, why do I say modified blow up? So let me just know this, enlarge this. So here are the two clusters, each with k vertices, and suppose there was an edge here in the original graph. So now what we're going to do is as follows. We're going to choose a random bipartition of the k vertices. So partition these k vertices into two equal parts, randomly, here and here. And we're going to put a complete bipartite graph here, between the upper parts and between the lower parts. And so between the cross edges are removed. Yeah.
Okay, so two questions. First, for each pair, so that for each of the set of k vertices, there's a different one for each.
Exactly. This is super important. Thank you for the question. So
it's different for each other one. Okay, and second, each of them, this might not matter, but each of them itself is an independent set, right? Like each of the sets of k vertices.
yeah. I put no edge. So the first question that Ryan asked was extremely important. I said that this is a random partition, but now let's consider another edge in the original graph. So now we have a new cluster, no edges within the clusters. So we're going to put edges here, but for the edges here, we're going to re-randomize. We're going to choose another bipartition, so it's high probability it's going to be, the two partitions here are going to be orthogonal to each other.
Those are not that orthogonal.
That's the best I can. Okay, and so basically we do this for all the edges of the graph, and this is it. This is a modified blow-up. It's a random operation on graphs. Here is our construction. You start with a small graph, say a single edge, and you iterate this, and at every step k is going to be exponential. So if you have a graph with x vertices, we're going to replace every vertex with 2 to the x new vertices. So the total number of vertices is going to be x times 2 to the x. So it's going to go exponentially, and we're simply iterating this r times. Okay, so let's just basic statistics on this graph. What is the number of vertices of this graph? So it's going to be tower of height r, roughly. This is number of vertices. Okay, and what is going to be the density of this graph? So we started with a single edge, which is a graph of density 1, and a modified blow-up, what it does is first blow-up stinks. A blow-up doesn't change the density, but then it removes half of the edges, right? So the density decreases by a factor 2 in each iteration. So the density of the final graph, which I'll call G, is going to be 2 to the minus r, right? Now, what we are going to show is that essentially, even after modifying this graph in 1% of its edges, any partition has to be, any regular partition has to be basically the trivial partition into singletons. Right? The partition into singletons, into vertices, where every part is just a single vertex, that's a huge partition, that's trivially regular. We're going to show that this is essentially the only regular partition for this graph. And so that means that every regular partition, its size is the number of vertices. So its size is going to be, its order is going to be tau of r. And if we want the density of the graph to be p, right? So we will choose r to be log 1 over p, and so we will get that the lower bound of the number of parts being tau of log 1 over p. So this is where the bound is coming from. Okay, so this is the very basic construction. Now let me just mention a few basic observations that will lead us to a sketch of the proof. So now forget about the fact that I iterate the modified blow-up, just for a single blow-up, okay? Just for this one modified blow-up. What would be a good regular partition for that? Well, here is a bad choice. I'll take the partition into clusters. So this would be all these k vertices are going to be one part, this is one part, this is one part. I claim this is a very bad idea. This is a very bad idea for a regular partition. Why is that? Just consider what's going on between those two bipartite graphs. What you see there is something which is very, very far from being epsilon regular, right? Because it has a huge subset of size half of this part, and half of this part that have density 1 between them in the modified blow-up. And then again you have this and that, again two large subsets which have density 0. So the density between this and that is 1/2. But you have subsets whose densities are 0 and subsets whose densities are 1. So that's definitely not 1/2 plus minus epsilon. So this is a very bad choice for regular partition. Okay, what about I'll take, this would be a part, the upper half, and this would be a part, the lower half. And I'll do the same for the rest. Would this be a good idea? Well, it will solve the problem that we have now, right? Because this part versus that part is a complete bipartite graph. This part versus that part is an empty bipartite graph, both regular. Cool. 0 regular. But now, let's consider another cluster. And recall that the bipartition here, the second bipartition, was randomly chosen, so it's going to be orthogonal to that one. So now we run into the same problem, because what was before the upper half is now no longer an upper half. Now it contains like 1/2 of the upper half here and one half of the lower half. Right? So this choice that we made for this partition was based on just this single bipartite graph, but there are many. So why take this choice? It's a bad choice. So okay, an obvious solution to that would be, okay, instead of taking those 2 parts, I'll take 4 parts. These 4 parts. Okay? In other words, I'll take the common refinement of the 2 partitions of these cluster vertices. Okay, so now we solved the problem with those 2 clusters, but then there's another cluster. So the point is that every new cluster forces us basically to refine our partition further. And since there are basically k other clusters,
Not K, X, whatever.
it's yeah, the original number of vertices before we applied the blow up. Thank you. So what we're getting is 2 to the x. Like we basically have to refine a partition with 2 to the x vertices, but k was chosen to be 2 to the x. So basically we have to. Our partition has to be the trivial partition into singletons. Everything was very, very roughly, but this is the gist of the construction. But this is far from being a proof, extremely far from being a proof. Okay. Who said, so I tricked you. Who says that we actually have to refine the cluster partition? Right, what I did, I tricked you. I said, okay, what about the partition into clusters? And then like the next options that I gave you were like refinements of that. So we took only like subsets of clusters. But why not? I don't know. Okay, so suppose that this graph is bipartite. Why should I? Okay, so these are now the clusters, each with k vertices. Why won't I take the following partition? This is one part, this is another part. Tiny partition, just 2 parts. Would this be a good choice? It actually very might be. Why? Because all the arguments that I've said here were basically, we have a large subset, 1/2 of our part, with density 0 to another part, or density far from what you would expect. But these subsets, which are like halves of clusters, they are half of a cluster, but relative to tons of vertices, like one vertex class of this bipartite graph, that's a tiny fraction. Right? If the number of vertices is larger than 1/epsilon, this is not even an epsilon fraction of this entire part. So this could not be a witness to the epsilon regularity. So it might very well be that here we have a bipartite, an epsilon regular bipartite graph, and we're done. So definitely, right, we wanted to show that every partition has to be of size 2 to the x. We have found a partition of size 2. So this is an issue. If you don't have to refine the cluster partition, then this entire argument fails. So who said we actually need to refine the cluster partition? Induction says though. So what the structure of the proof is to inductively argue that you start with some partition, and then you apply the modified blow-up, and now we know that every regular partition has to basically be the trivial partition into singletons. But now we apply the modified blow-up again. Now every singleton becomes a new cluster, right, after the blow-up. So we know that this so we have basically a partition. By induction, our partition has to refine these clusters of the new graph, of the modified blow-up of the current graph. Okay, so at each step, we are assuming by the induction hypothesis that our regular partition refines the previous clusters, which were singletons previously, and we deduce, and then we apply an argument similar to what we did here to deduce that we actually need to refine the clusters of the next iteration. This is
every regular partition looks like this. That's what you.
Every regular partition is going to look like this, meaning the trivial partition. This is still very far from a proof. Two major complications. So I tricked you, there were two tricks that I pulled on you. Another trick was that I only considered, like I told you, okay, we have this modified blowup and this is our graph. But actually our graph is not a modified blowup. Our graph is an iterated version of that. So the final graph is what happens after you have to apply R times that. But all of these arguments, when I said you have density 1 and you have density 0, but this is not going to be density 1 forever, because in the next subsequent iterations, this is going to decrease. The densities are going to change. Who knows what happens when you apply the modified blowup multiple times? So everything that I said here was basically cheating. This is one complication. Another complication is that
You use the fact that epsilon is actually the power of P, so
it's still not enough. It's still not enough.
it's important, I think. I don't know if it's enough, but it's important that epsilon is some much smaller than P.
Of course, the regularity lemma with epsilon, the regularity lemma, epsilon must always be smaller than P, otherwise this notion doesn't.
Yeah, but I agree, but it's not important for this proof also, for this.
Yeah, you can't prove a lower bound for, yeah. Another complication is that, okay, I forgot to mention, very conveniently, I forgot to mention that when someone tries to find a regular partition, he can actually not work with the graph that I constructed. He can actually change it considerably, like 1% of the edges, do whatever he wants there. And our arguments still need to work despite those modifications. So these are two very major complications. So let me give you, in the 5 minutes that I have left, like a vague idea for, so how do you approach these complications. So let's denote by calligraphic xi the partition of the final vertex set of the graph, which is of size tower, right, into the clusters in the ith partition, right? We call that, so in the ith iterations, those were like the vertices, and then we blew them up. So this is still, so now this single vertex become a set of k vertices. So now we have a partition into clusters. And in applying the modified blowup again, we get another partition. So this is like a sequence of consecutive refinements. So again, xi corresponds to the vertices in the ith modified blowup, in the ith iteration.
These are supposedly the best partitions possible.
Basically, you have to basically, in each step, so this is like a reverse engineering. Basically, in every proof, you would have to follow some iterative process and stick to those partitions roughly. But importantly, what we have to do is to keep track of what happens to every part. So recall that our lower bound matches the upper bound. So our proof has to be really, really tight. So we have to keep track of everything that happens. But what do I mean by that? Or what do I mean specifically by the evolution of a part? Consider one part. So we give given this graph, we try to find an epsilon regular partition, calligraphic P. Take any part of this supposedly regular partition and see where it's. So let me use another color. So this is going to be P. This is P. Now, P sits within this cluster completely. But then once you move to the next iteration, this is further partitioned into many small parts, exponentially many. So now P, if I zoom in, it might be the case that P sits completely within one of those clusters. But it also might be the case that P has a few vertices in another small cluster. Another option could be that in the next iteration, P completely shatters. So P no longer has one part in which it's mostly contained. P is basically broken to bits and pieces all over, completely shattered. What we're going to do is we're going to, for each part, we're going to see, to keep track when is the last time that it's mostly contained in one of the parts of like one of the partitions xi, one of those canonical partitions. because after that it might be completely shattered and our arguments would completely fail. So here is the key property of our graph. Suppose that this part P breaks off first at iteration I, meaning that, okay, so what is this notation? By this I mean C is some constant, and by this I mean that in the partition into those big clusters xi minus 1, the part P is mostly contained in one of them. So P is mostly contained, maybe it has some vertices here, but P is mostly contained in one part of xi. Mostly contained meaning that the fraction of P that lies within this one part is at most C fraction. The number outside is at most.
The number outside
is at most C times the size of P. But this is no longer true for the refined partition xi. So now outside of the main part that contains P, you have more than C fraction of P. Potentially, there's no one part which P is contained. Potentially, P is completely broken, completely shattered. So it can be shown that there are 2 to the minus, so I is the iteration that this happens. So there are 2 to the minus I fraction of the good clusters, of the clusters that are good. Clusters in the ith canonical partition, which are good. Good in what sense? That the density between our part and those good clusters is up to a constant, what you would expect, but there is a large subset of P that has 0 density to one of those good pairs. And this is tricky to prove for various reasons. One of the reasons is that, okay, at iteration iteration I, P might have vertices all over the place in various clusters from previous iterations, who knows what. And I'm going to need to collect many of them and to argue that for many of them, like constant fraction, I can argue something about the density between them and a nice cluster. So this is kind of technically involved. But once you have this key property, and I will make one assumption for simplicity, I'm going to assume that each of those good clusters happens to be exactly a part of the partition that is supposed to be epsilon regular. This is not necessarily a realistic assumption, but let's assume that. Well, but what can we say about the bipartite graph between P and Y? They are both parts of the partition P, and so that means that they have to be epsilon regular, P to the 10 regular, after some modifications. Sure, some modifications are allowed, but this bipartite graph has to be regular. But because you have such a large subset of such small density, it's not hard to see that in order to turn a bipartite graph like this, the bipartite graph induced by P and Y, in order to make it regular, P to the 10 regular, actually just P over 10 actually would also be fine. You actually need to modify constant fraction of the edges there, basically. This T to the I times P. Forget about the quantifications, I don't have time. Like, why it's 2 to the I times P, why this is what you would expect, never mind that. And now sum over all good i's, this is the number of good i's. So you multiply this by that, so the 2 to the I cancels, and so you have P times the size of this part P times the size of Y times the number of clusters in the ith iteration. Okay, so this is the size of one part, and this is an equatable partition. And so the size of one part times the number of parts, so this product is just the total number of edges, n. So if you sum all of these, you get P times Pn. So in other words, not yet. The number of this shows that the number of modifications that you need to do in those edges that are adjacent to P is this. Like, this is the average degree times P. So this is basically the expected degree. Actually, it's going to be a degree regular graph. So this is actually the total number of edges adjacent to P. So we have to modify a constant fraction of that number. Now we sum over all possible P's. Many of them would have to satisfy this property that they break at some iteration, can definitely be different iteration, different i's for different P's. but from each iteration we still get that. Okay, so I don't care what happens to P during the entire evolution. In the last step before it shatters or not sufficiently contained in one of the canonical clusters, we are gaining this much to the number of modifications that have to be made, and if you sum over all of this, you get a constant fraction of the edges. This constant will set it to more than 1%, and we're done. Just one thing to notice is that this was a very convenient assumption to assume that those clusters, good clusters Y, were parts of P. If they actually can be decomposed into parts of P, then this argument actually works. But it definitely might not be the case. So you would have here like bad vertices of Y that don't belong to any big chunk of P prime and other P's, and then you have some bad vertices, and you need to make sure for these arguments to work despite the bad vertices. You need to make sure that the bad vertices don't have too many edges going from them to the vertices you are interested in, which is actually true, assuming that our graph is somewhat quasi-random. Our graph as a whole, our entire construction should be also quasi-random, which seems like a contradiction almost, right? Because we want to argue that the graph, every regular partition has to be large, has to have many parts, but if the entire graph is quasi-random, then we're done. We take it's a bipartite graph, so take its two vertex classes and we're done. So where's the contradiction? The thing is that the quasi-randomness that we need here is a notion which is weaker than even P2/10 regularity. So this is a very weak notion of quasi-randomness that the entire graph satisfies, and it's important that it's not too quasi-random, but it has to be at least somewhat quasi-random to handle those bad vertices that I mentioned here. For the full proof, you can see the paper. It's maybe 20 pages, I think. Okay, I'll stop. Thanks.